Okay, let's see if I can go a little faster. All right, so this is some of the applications of spectrophotometry. All right, so the absorbance of a solution at any wavelength is going to be the sum of the absorbances of all the species in the solution. That's pretty straightforward, right? So if you have 3 species that absorb at that wavelength, what is the overall absorbance of the solution? The sum of those 3 things, right? This is what that looks like. It's literally just a Beer's law for each species, right? They're additive, so they just add straight together. By the way, the reason they're straight up additive is because you're in absorbance. So if you ever need to figure out how large each peak is from each species, you always need to be in absorbance. Do not try to do this in transmittance. It will not work correctly because it is a logarithmic scale. You would have to have a logarithmic equation. Okay? That makes sense to everybody? Okay. All right. So what to do when the individual spectra overlap of these different species? Well, first you would measure the absorbance of each standard at several wavelengths. You'd record them in Excel along with concentrations of the standards and the path length of the cell. Essentially, you're setting up Beer's law for your different species, right? And so this is essentially what this would look like, okay? So you see here you have 3 different species. They all overlap to some degree. See that? Now note, the peaks are not in the same place. They almost never are. It's very unusual for the peaks to be in the same place, and that could cause some really interesting effects, by the way, but they never are. Like, I've only seen it once in my entire career of thousands of spectra, okay? And it caused some interesting stuff. Anyway, see, the peaks are actually in different places. See that okay? Okay. All right. So this is what that looks like. So you do different standards at these different places. You take the different absorptions, the different wavelengths. So when we calculate the molar absorptivity using Beer's law, X would be titanium here, Y would be vanadium. A of X is the absorbance of the standard, and X is the concentration of the standard. Is that okay? And, you know, concentration of standard. And remember that X is your titanium, right? Okay. So this is your extinction coefficient. You're going to need it for your Beer's law. You would take, you're just solving your Beer's law here. See that? We've taken absorbance of that species divided by the path length times the concentration of that species. You see that okay? You set this up to have standards in here. Notice these are your standards right here. There's your path length. Okay? You would also set up the same sort of equation for your other species, which would be vanadium in this case. This is 2 species. Okay. Everybody see that okay? Fantastic. All right. These are the absorbance of the standards, your molar absorptivities that you calculated here. This is the measured absorbance of your mixture. This would be your calculated using the Beer's law that you just calculated from your standards, right? And what we see here is we take the differences. See, that's the absorbance calculated minus absorbance of mixture. We square them. And these are the values we get here. We would then take the sum, which is that right there. All right, so the measured absorbance of the unknown mixture is right here. That's that A of M. This is at each of these wavelengths. See that okay? So again, this measured absorbance here. What is that? Well, that's the sum of the Beer's law for each species, right? At that wavelength. So that's the sum of the absorbances of each species. We don't know the concentrations of X and Y in an unknown species, right? In an unknown sample. So this mixture sample, we don't know those. But we can guess the values of these here. And so these are the guesses right here. Those are found by our solver. We go ahead and set up our solver with these factors, with our wonderful equation here. We have a 2-variable. See that? And we let it solve to generate the absorbance calculated, which should match as close as possible to the absorbance of our mixture here, right? Is that okay? Fantastic. Notice we have plenty of equations to solve for 2 variables, don't we? See that we have 1, 2, 3, 4, 5, 6 of them, right? No problem. Okay, that solves out to give us a 0.001 molarity. So our last column here is going to show the square of the differences between the calculated and measured values. These would be your square differences, which would be your accuracy of your measurement, right? So we take the calculated minus the measured right here. We would square it, so we get our square differences. Again, whenever we're doing the least squared fits, the least squared condition is always to minimize the sum of the squares by varying X and Y concentrations, right? So the best values are those that minimize the sum of the squares. That would minimize this value here, right? That would give you your best calculation. So what you want to do is you want to calculate the sums of these red column, highlight it, and then select our solver. Okay? And what we're doing is we're aiming to get this as close to 0 as we can, right? And so that would then be what we're solving for, is to minimize this sum of squares, right? Same as a least squares fit. Okay. All right, so again, the H11 is going to be the cell showing the sums. Where the hell were we? You would select min and the cells containing the 2 guess values. These guess values are what we have to start off with, right? We're going to assume that they're fairly low concentrations, and that would be why we guessed, I believe we guessed 0.1 if I remember correctly, or no, 0.001, right? Essentially, you want to start off as something pretty low, okay? The reason we start off at something pretty low is because our absorbance values are fairly low, right? See that? We don't have like 0.9, do we? Okay. Anybody have any questions so far? So this is all the setup here, okay? We plug it in, so our solver is solving for these by minimizing this. This should get as close to 0 as possible, right? Using this data here. Okay? These are actually just going into here, okay? Okay. And what we see here is that this is the results of that solving. So the solver has minimized this value to 10 to the negative 5. That's pretty decent, right? That's a value very close to 0, okay? And what it's gotten is concentrations here from that solving, okay? These are just the millimole values, 10 to the negative 3 versions of those. This is in molarity down here, okay? Anybody have any questions? Nothing? Okay. What would this look like if you wanted to do like a 3 or 4 species one? Would it be particularly different? No. It would just have another column here and another column here, right? Yeah. And so you do another set of standards. You'd have another column with their absorbances. You'd have a calculated absorbance here that would now be different. Your measured absorbance is whatever you measured, right? For your solution, whatever the hell that was. Apparently have 3 species in that case, right? And again, you would have another set of these here, right? And this wouldn't change at all, would it? Because the third species would be in this calculated term here. It'd be embedded into it. So we'll still have an absorbance calculated versus absorbance measured, right? And a least squares thereof. We would just have one more term down here, whatever that third species is, and we'd solve, right? How about 4 species, 5 species, 6 species? Yeah. Eventually, we would have to start getting more standards in here because we wouldn't have enough variables, okay? So we would need more standards so we could fit this properly, but yes. Yeah. Remember, you always should have at least one more standard than you have species, okay? Otherwise, you can't get a unique answer out. All right, so when the spectra of the individual components of a mixture are moderately resolved from one another, 2 simultaneous equations can be solved to find the concentrations of each component in the mixture. So we get the lambda prime, 447. This would give us this absorbance. These primes are literally like a numbering system, okay? So we get our first lambda here, our second lambda here. All right? Typically named prime and double prime, in case you're ever curious. The reason you have these different values is because you'll have different absorbances at each wave number, right? Or a wavelength in this case. So this will give you a different absorbance than the 600 nanometer one would. They also, this is because the absorbance comes from the extinction coefficient, right? And your extinction coefficient is different for each wavelength, okay? So you can never use the same extinction coefficient for a different wavelength, can you? It always has to be different. Okay. So the molar absorptivities of compounds X and Y at each wavelength are measured with pure samples of each compound. You can solve for the 2 unknowns, X concentration and Y concentration. Essentially, you're setting up Beer's law for each unknown, right? So each species the unknown, you're setting up a Beer's law. You can solve it then for the extinction coefficient, and that will give you a way of measuring that absorption due to that species. So here we see a mixture of compounds X and Y in a standard cell, 1 centimeter cell. We find an absorbance of 0.957 at 272 nanometers and 0.559 at 327 nanometers. You would then find the concentrations of X and Y in the mixture. Okay. These, in this case, we have molar absorptivities for each of these species. See that? So at this, these are the molar absorptivities. At this, these are the molar absorptivities. So all you would do is you would just take your Beer's law, set it up for each of the absorbances. So for this wavelength, we would get an absorbance, that value right there, right? Which would equal the molar absorptivity for this species times 1 for the path length. And then you'd have a variable of the concentration of X here, right? And then you would have the same thing for y. They would look just like these equations here. We've given you this values. All you would have are these variables here, right? Note that the concentration of x does not vary. The concentration of y does not vary. So if you solve it, so one term is on one side, you can plug one into the x, right? And you can continue doing that until you're done. Or you can do it the much easier way, which is set up one of these spreadsheets and just change the variables in. Once you get it set up, you can do, hundreds of these every few minutes, right? Yeah. Which is how I did it. I'll be honest. So again, Excel can be used to solve simultaneous equations. This is definitely the way I'd recommend doing it. I would not recommend solving one for one variable and then plugging it in over and over and over. The solver is definitely much faster, much easier to do. Excel is much easier. So again, these are the equations and what they look like. So in our previous example here, see our example we just talked about, we would get, again, this absorbance here, see that? The 0.957 is the 272 nanometer absorbance. That would equal the extinction coefficient times 1, which we don't have to list, right? This is times 1, times the concentration of species X, plus the extinction coefficient times the concentration of species Y. Everybody's good with why this has a different absorbance and a different extinction coefficient for this absorbance double prime, right? Because it's a different wavelength. In this case, it's 327 nanometers. Okay. So this can be written as a matrix as well. This would be the matrix notation. This is actually the easier way to use math to solve this if you were ever to do this. And this is actually closer to how the computer does it, in case you're curious. Because computers can do matrix calculations very easily. Okay? So this would be the matrix calculation. So you have a matrix of your absorbances, the first and then the second, right? Your two different wavelengths. You then have the molar absorptivities or extinction coefficients, which are these values here. It's each wavelength for the two different species, right? And then you have a matrix of your unknown variables, which are your concentrations of the two species. Everybody see that okay? Has anybody learned matrix calculations at all in their math? No? Okay. I'm not surprised, to be honest. It's sad that every freaking university, almost all of them, except for a very few very elite ones, teach you calculus, but they don't teach matrix calculations. They almost don't cover it at all. And it's sad because you can do everything calculus can do with matrix calculations better. You could program it and do it with a computer. So it makes them very short, very easy to do. So like calculus is kind of a shitty thing. It's useful for a lot of like theoretical math sort of stuff, but it's much less useful to actually get results. Anyways, does anybody have any questions about this so far? Okay, so I would use Excel with a solver. To solve the simultaneous equations, you would find your inverse of your matrix K, so K to the negative 1. Your matrix K is literally just your coefficient matrix. It's essentially the terms for your B, which is path length, times coefficient, right? Your molar absorptivity or your extinction coefficient. You guys okay with that? Notice these are the wavelengths form. You would then have the matrix here, which is A, which is your absorbance right there of the unknowns. And then these would be the concentrations, the mixtures, and those are the ones you're solving for. Okay? That's your product. All right. This is how you would do it here. So you'd enter your matrix here, which are in these cells. You'd enter the absorbances of the unknown at each wavelength, which are these cells here. You would then highlight the block of blank cells right here that you want filled, right? You would then type formula equals M mult, parentheses, minverse, B5C6. Again, that's this area right here, right? Comma, D5, D6, which are these ones right here. This is going to essentially solve for two variables here from those results. Okay? Typically, you should be able to, for almost all versions of Excel, on PC, you would hit Control-Shift-Enter. On Mac, it would be Command plus Return, I believe. They should work. If they don't work, you may have to look up what those new commands are in your new version of Excel or your old version of Excel, whatever. You know, just Google it. That always works. Okay? But those are the commands in the version of Excel that I'm most familiar with and your book would be familiar with. Your answers would then pop into here because it solved it for you. If you had to solve this, you could solve for one, plug it in, solve for the next. Okay? It just takes 10 times longer than doing it this way. If you understand what you're doing, this is like a minute of work, right? Maybe half a minute. Okay. Isosbestic points. So one absorbing species, X, is converted to another absorbing species, Y, in the course of a chemical reaction. If the spectra of pure X and pure Y cross each other at any wavelength, right here, then every spectrum recorded during the chemical reaction will cross the save point. This is called isosbestic points. So you can actually see this in operation here. See this, this species here is reacting. See that? And we're forming this. Can you see that okay? So these two species are linked together with a reaction. And you see as one goes down, what happens to the other? It goes up because they're reacting. And you see the point in between where they cross? Every single spectrum of those crosses at that exact same point, doesn't it? Same height, same X, same Y, same point. Cool, huh? And that is true anytime you have two different wavelengths that represent two different species. Okay? And they're in a reaction with each other. All right. So this is actually an evidence that only two species are present. Because if you had more than two species, then you wouldn't have a singular point like this, right? The two observing species have the same molar absorptivity at that wavelength. So, this is what you get right here. So, at that wavelength, the absorbance of, at 500, which if you look closely, that's at 500 nanometers, right? That's what the absorbance at 500 means. Your extinction coefficient at 500 for this species would be like so. Your path lengths are the same, of course. And then your concentrations would be due to the reaction, right? So by definition, your extinction coefficients have to be the same at that point, at 500, for you to have one of these wonderful points, the isospecific point, right? Note that you can simplify your Beer's laws like so, because these terms are common for both of those. So the only thing that's going to be changing is your absorbance due to the concentrations, right? But your absorbance actually ends up being the same throughout this entire process. Why is that? Because this converts to this, doesn't it? So this overall term has to be the same all the time. See that? Neat, huh? Okay, so let's talk about a scratchard plot. We'll examine the equilibrium in which the species P and X react to form PX. So right here we have reaction, P plus X gives us species PX. If we neglect the activity coefficients, we can write the reaction equilibrium equals products divided by reactants, right? Notice again, our activity coefficients are being neglected. We don't have any powers up here, do we? Okay, so the increments of the antigen X, by the way, this is a very common way to do like protein binding antigens, that sort of thing, okay? This example specifically is for an antigen and an antibody, okay? So the antigen, which is our X here, are added to a constant amount of the antibody P. So this is the antibody P right here. Where P0 is the P total. Essentially, this is telling us we've added the antibody in. The amount that we started with would be our total amount of antibody. Okay? The amount of P present before any X is added would be, well, the total concentration equals the P0 minus whatever antibody we make, right? Whatever bound antibody we make. So the equilibrium expression actually can be rearranged to this right here due to the fact that we know these terms. So what do we get? Well, remember that the Px over X would equal K times P. All we've taken is multiply P over, right? See that? For equilibrium expression, we've multiplied P over to get this term right here. Well, then we substitute this term here for P0, which is a known quantity, which we can just plug in, right? Minus Px. Notice that shows up twice now. See that? So we've simplified this term for doing calculations later on. So now, a plot of Px over X versus Px. So Px over X would be our Y. This right here would be our X, right? Can everybody see that okay? So we made essentially a linear relationship out of our equilibrium expression. So that plot of Px over X versus Px, it would have a slope of negative K. That's our slope right here. It's called a scratchard plot. And so that's the scratchard plot. We can plot these values versus each other, and we'd get a slope of negative K. Why would that be interesting? Well, K is our equilibrium constant, right? So this would be a way of determining equilibrium constants in a wide variety of biological, biochemistry fields. So again, this is going to be widely used in the biochemistry field to measure equilibrium constants of these different protein bindings, antibody bindings, these sort of things. Okay? If we know Px, we can find X through the mass balance equation. So whatever amount of the, so remember, because we had some people leave during this, let's review this really quick. Okay. So the antibody is the P, right? The X is the antigen. So if we set this up in an experiment to determine this binding, we know the P that we started with, right? Because it's what we added. We know the X that we started with because, again, it's what we added, right? So if we can determine PX, then we always know how much is in each form of it. Because there's only two possibilities. There's PX and X, right? And those always have to sum to whatever X we put in, doesn't it? Okay? And that's called the mass balance equation, of course. So whatever X we put in is the total amount of X that's possible, right? And it's between these two different species. If we know PX, then we know X automatically. So, how the hell do we get PX? Well, we have, remember, we have all these spectroscopic techniques now to determine concentrations, don't we? So what do you think we're going to use? Spectroscopy, of course. Specifically, it's applied spectroscopy, so spectrophotometrically. We can measure the PX. Typically, what will happen is P and PX have some absorbance at wavelength, which would be lambda, that's your wavelength. But X has no absorbance at this wavelength. And of course, you would keep your path length constant. Typically, these path lengths are 1 centimeter. That's the standard 1 centimeter cell that you guys have seen lots of. And so we get this same relationship. We started this chapter off. The absorbance equals essentially the Beer's law for each, right? Okay. Note that we can always remove the B term if we set it to 1 centimeter, right? Because then it's times 1 for everything. So are you guys comfortable with the B term is gone? Because it's 1. That's why that's standard 1 centimeter path lengths. Okay. Okay. Okay, so again, that's the total absorbance equals the extinction coefficient times the concentration for each species, right? Well, we now have a relationship between P and PX, don't we? And that relationship is the P total equals P plus PX, right? So we solve that for one term so we can plug in the other two into it. So we've solved it for P to give us P0 minus PX. Why did we target PX? Because PX is related to everything, right? It's related to P and it's related to X. So once we have PX, we have everything, don't we? It's all simple math after that. So we've then go ahead and plug that in, variable exchange, and we get the absorbance equals the extinction coefficient times PX plus the extinction coefficient for P times P0, what we started with. By the way, this is a term that you can measure. This is literally just the absorbance at time 0 before you put any species X in, isn't it? So as long as you know what you're doing, you can literally just put P in, measure the absorbance, then put X in after, and you'll have this term here. See that? Okay. Which you'll probably have to do anyways to get the blanks and such. All right. So then this is minus the extinction coefficient of P again times PX. Notice now we only have one concentration that we need to solve for, don't we? We can measure this. This is measured. These are values we can get from doing the standards and a Beer's law, right? So again, A0, which is this term right here, that's the absorbance before any X has been added. We can rearrange this to simplify it so it looks like a linear equation. So the absorbance equals the concentration of PX times the extinction coefficient PX minus the extinction coefficient of P plus the absorbance at time 0. This essentially gives you Px equals the change in absorbance over the change of extinction coefficient. So, again, the change in extinction coefficient is this term right here. See that? It's the extinction coefficient for Px minus extinction coefficient for P. The change in absorbance is these terms here. See that? We've just rearranged them. So the absorbance minus the absorbance at time 0, or initial absorbance, before you added any of the X species. So again, we can do a nice Scatchard equation with a nice Scatchard plot, can't we? So again, we can measure the absorbance while the P is titrated with X, use a graph of the change of alpha, the change of, alpha, the change of absorbance over X, as we add it, versus the change of absorbance. This will get us the equilibrium constant of the reaction of X with P, which is what we're looking for, how well that binds, right? This is the equation that matches up with this Scatchard plot right here. So again, the Y is this right here. See, that's that change of A over X. The X value is this change of A right here. The slope is negative K, which is the equilibrium constant. Notice the y-intercept is actually the equilibrium constant times the change in extinction coefficient times P0. So if you had to solve for those, which I have never actually had to solve for them, but that's where those terms are, in case you're curious. All right, so let's talk a bit more about using solver. So riboflavin, vitamin B2, this is essential for energy production and biosynthesis in many types of cells. Here's riboflavin, vitamin B2. Neutral red is a dye with a structural similarity to riboflavin. It binds to riboflavin binding proteins, and so this is neutral red. It's an analog of riboflavin. You can actually see the analogous portions, can't you? It's visually quite analogous, which is nice. We want to determine the equilibrium constant, K, for the formation of the protein and neutral red compound. So here would be a protein that would normally bind to riboflavin. We're binding it with neutral red. This is how you would set this up normally. Note, by the way, P was always used because the most typical way of using this is for protein, right? And then X is whatever the hell the protein binds, right? And it forms some complex. Typically, these are 1-to-1 binding, by the way. And so this works out very nicely because its coefficients are all 1, right? Okay. We get that same equilibrium expression. So increments of P are going to be added to a fixed quantity of X, and okay, let's go ahead and quit here. And we'll start up here next time.